You're on the air.
Huh? What?
What was that? We're on? Oh, hello folks. Welcome back to the show. In case you're just joining us, I'm Esteban.
And I'm Philippe.
Shut up!
He's Jesse, the intern. He'll help us out with the visual aids.
So anyway, we will now be discussing the intriguing topic of muscle contraction. Philip, what do you know about muscle contractions?
Well, muscle contraction is controlled by the part of the brain called the primary motor cortex. The primary motor cortex is located in the frontal lobe and contains neurons that have long axons that go down through the spinal cord and synapse directly with the anterior horn cells, which connect to the muscles. When you want to contract your muscle, your primary motor cortex tells your muscles to do so through a signal called an action potential.
Well, isn't someone here, little smarty pants? I don't think the audience even knows what an action potential is, so here it is in a nutshell. The inside of the neuron membrane during resting state is negative, while the outside is positive. Once a stimulus occurs, the sodium channels in the membrane open rapidly, allowing sodium ions to rush into the cell. This flood of sodium ions continues in that local patch of membrane until a threshold is reached and depolarization becomes self-generating, creating an action potential. Sodium permeability increases 1,000 times, causing the voltage to overshoot into a positive voltage.
Then comes the depolarizing phase. During this phase, there's a decrease in sodium permeability and an increase in the potassium permeability. The sodium channels are now closing and potassium gates are opening up to allow potassium to rush out of the cell to reestablish a net negativity of the inside of the neural membrane. This process occurs all the way down the axon, where it is converted into a chemical signal at the axon terminal to pass on to the next neuron, and then converted back into an action potential.
Now this is where the action potential reaches the muscle. The action potential arrives at the neuromuscular junction and is propagated along the sarcolemma of the skeletal muscle. The action potential is then propagated down into the muscle cell near the end of the sarcoplasmic reticulum by the T-tubules.
This causes depolarization, which makes the voltage-gated calcium ion channels of the sarcoplasmic reticulum to open. This increases the permeability to calcium ions, which diffuse from the sarcoplasmic reticulum into the sarcoplasm.
Yep. Now in a muscle, the thin actin and thick myosin filaments are juxtaposed but cannot contract because of the fact that the bonding sites on the actin are covered by a protein called troponin. The calcium-sensitive troponin are attached to the end of each of the tropomyosin.
Now remember, action potential increases calcium levels. The calcium ions bind to the troponin and move the troponin off the myosin binding sites. The myosin heads can now bind and form cross bridges and create a contraction in the muscle. The muscle relaxes again once ATP binds to the myosin to release it from the myosin binding site, and when calcium ions are returned to the sarcoplasmic reticulum by calcium pumps.
Yep, that's pretty much it. Not too complicated, eh?
Nope, not bad at all.
Well, until next time, stay healthy.
And smart.